So good morning. This is a second lecture in which we touch on a topic that is intrinsically related to quantum chemistry. In the previous lecture, we looked at the theoretical model for um, hydrogen molecule. And today, instead, we look at a model for a rather more general feature of chemistry. It concerns ionic covalent binding. So this is, if you want, the simplest possible example of covalent binding from the point of view of quantum mechanics, because it involves one electron being shared between two atoms. Now, this notion of electron being shared between atoms is something we hear a lot about in the early college education, late high school education, as the sharing of the electrons being somewhat at the base of quantum chemistry, of chemistry and binding, covalent binding. At the beginning of this course, I remember I tried to motivate, excuse me, I tried to motivate the interest in this course by saying that one of the fascinating features we shall discover by studying quantum mechanics and quantum chemistry is the very nature of molecules, the very existence of covalent bonding has to do with intrinsically quantum phenomena, and in particular, rather exotic quantum phenomena, such as quantum tunneling. We discussed quantum tunneling, if you remember, when we were talking about two-state systems where the particle be in the left or in the right state and being able to tunnel through the barrier. And I am aware that if I say another time something with a fake inverted commas, I'm going to be expelled from my role of lecturer at the University of Trento, so I'll try not to do that anymore. But that's basically, passible of death penalty 3 times in the same lectures. But yes, it's something that goes as if the particle, in this case, the quantum mechanical particles, were going below the barrier, jumping out on the other side, hence the name tunneling. So one of the interesting features of today's lecture is that we shall elaborate on this connection and show that, in fact, the simplest model for ionic covalent binding does involve kind of a form of tunneling. To do that, let me remind you that when we were studying this double well system, we were playing a game. We were expanding the solutions of the wave function for the ground state or first excited state, so n is equal to either 0 or 1, as a linear combination of left, C right, and right states. But these are functions, maybe Gaussians, locally approximating Gaussians localized in either the left or the right state. Remember that. Then actually the 2 coefficients here were kind of relative. Having to introduce 2 coefficients was kind of redundant, because one of them was effectively reabsorbable into a normalization. So then what we were doing at the time was showing that you can diagonalize the Hamiltonian in this truncated basis approach. So what we were doing, we were constructing an Hamiltonian matrix, left, 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 right, right, left, right, right, where H left, left, for instance, was like phi left, H phi left, and so are the others. So basically what this approach was showing was the power of the truncated basis approach because by diagonalizing directly these 2 by 2 matrices, we were able to show that there were 2 closely, nearly degenerate eigenstates here, 1 and 1, and that, you know, the ground state and first excited state were supposed to be. Phi left plus phi right, and phi left minus phi right. Again, we were making some approximation and working out all this. In particular, we were interested in neglecting the overlap of the wave function here as far as the normalization is concerned, or the orthogonality of the function. So there were some here and there, some kind of a simplification schemes, but the overall approach was that of studying tunneling through a truncated basis expression. So having reviewed all that, let's see how that can be used to study covalent binding as well. Okay, a central concept here that we shall introduce in order to describe this is a seminal idea that goes under the name of molecular orbital theory. So what is molecular orbital theory? Molecular orbital theory is an approach according to which the wave function for your molecular system can be written as a linear combination of coefficients in which the electron is, you know, these are the orbital of the electrons in each of the atoms of the system. So these are the atomic orbitals. So remember, what are the atomic orbitals? Are either S or P wave states that compel the last electron, in this case, that I feel after I, you know, employ mean field arguments to fill all the orbitals and have a bunch of electrons, you know, piling up energy levels according to the Pauli exclusion principle. And this may be, for instance, an S wave or a P state or D states, in which case we know exactly the function, say, for an S state, NS state, the molecular orbital will be the nth radial excitation times 1 over root of 4 pi. Because it's an S wave, there's no spherical harmonic. If I have a P wave, then there would be the nth radial excitation times L equal 1, and maybe M equal 1 or 0 minus 1 state of the orbital harmonics. And which one I use is predicted by the underlying orbital, electronic orbital theory that tells me, you know, where am I in that particular atom in my process of filling all the orbitals and shells by putting the electrons that I need to put in order to obtain the right number of the correct neutrality for that atom. So these functions here are atomic orbitals associated with the different atoms involved. In case of molecular orbital theory, there are only 2 atoms, ionic covalent band, and there are 2 atoms. Let me call it A with charge Za and B with charge Zb. That's E, of course. And there's 1 electron. And the idea of molecular orbital theory is, in fact, the electron is not in an eigenstate of either of the 2, but rather is in a superposition of states. That's what this is. That's what's written there, right? That the electron is in a quantum superposition of states of eigenstates of either atom A or atom B, which, if you think quantum mechanically, simply means that anytime you perform a measurement, you can find the electron either in A or in B with certain probabilities given by the square modulus of the corresponding coefficients. So in some sense, by assuming that the electrons is in a quantum superposition of both states, you can map this problem with a barrier here and say, it's like if the electron was constantly tunneling between one atom and the other. And by going back and forth in this quantum tunneling journey, it generates quantum superposition of states. Basically, is neither the eigenstates of one or the eigenstates of the other. It's like somebody is involving with, a guy with two girlfriends or a girl with two boyfriends, sharing days with them, like in Italian comedies from the 70s. There's always this guy with a wife and a mistress going back and forth, catching the bus and pretending he's in one place and being in the other. So that's a macroscopic way of doing delocalization. The electron is probably doing something very similar, is simultaneously in a relationship with both atoms, trying to maintain this relationship by hopping from one atom to the other, without hiding in the closet in this case. Okay, so that's what this linear combination is actually stating as a physical model. The idea is to use the variational principle essentially to determine the best coefficients. That is, write this as a postulate, calculate the expectation values of the energy given these linear combinations, and then perform a variational optimization of the coefficients, which basically amounts to saying, I'll find the best combination of orbitals given the best wave function restricted to the subspace of the Hilbert space of functions that are constructed out of linear combination of atomic orbitals. So the approach is in fact quite simple. We shall consider only two molecular orbitals in this case, because there are only two atoms. So my wave function psi would be C1 psi 1, this is the first atomic orbital, times C2 psi 2. And so this is actually phi 1 and phi 2. And in addition to that, my phi 1 and phi 2 are the two orbitals. And of course, there will be the same orbital, because I'm assuming for the moment that these are identical atoms. If they're different atoms, then there could be different orbitals. So let's take the most general case. Okay, so now in order to evaluate the expectation values of the energy, I need the Hamiltonian. And of course, the Hamiltonian is going to be the kinetic energy of the electron plus the repulsion between the static nuclei. Remember, we are in the Born-Oppenheimer approximation. That's the distance between the nuclei. And the attraction of the electron to either of the atoms. And of course, this attraction may be different because they have different charges. The electron may be married to atom A, large charge, and just engaged to atom B. So one will eventually have to do these calculations of computing the matrix element of the Hamiltonian between different orbitals. So let's move on, and let's include the normalization. The normalization stands in front, and we're gonna simply work out the normalization so that we don't have to worry about that later. So now, if you assume that each orbital is normalized, and you want to impose that also this function is normalized. Now, this would be a multidimensional position. That's actually three-dimensional position of the electron, right? So if I assume that this is actually normalized, Then I will get like n squared, and I will get, for instance, C1 square modulus square integral of phi 2 star phi 2, that's going to be 1 plus C2, oh sorry, phi 1 square, C2 modulus square integral the phi 2 star 2 plus the cross product C1 star C2, the overlap, and C2 star C1 phi 2 star phi 1. Okay, that's what the, this is all about, and this is 1. This is also 1. I already wrote there. So really, the only term that I'm missing is this overlap S12, or let me call it S. So S, I have to work out some space for it. So basically what we arrived to the conclusion is that 1 over n squared, the normalization squared, must be equal to C1 squared, modulus squared, plus C2 modulus squared, plus 2 C1, C2. Well, you have, if C1 and C2 are complex, then in principle you have C1, C2 star, C2 star, C1 star, C2. But let's assume C1 and C2 are real for sake of simplicity. I think you can do that if the Hamiltonian is real without any loss of generality. And this multiplies this matrix element S, and the matrix element S is in fact phi 1, phi 2. Again, assuming the orbitals are real, I don't have to worry about S being complex. If the orbitals are not real, then in principle I have to worry about complex, and then all I have to do is to write explicitly C1, C2 star, P1, phi 2, and then the other one will be phi 2, phi 1, and so you'll get S and S complex conjugate. But let's not worry about complex conjugation here. Again, you can assume safely that the orbitals are all real. So what is the result? The result of this wave function will be, the expectation value of the energy will be psi h psi divided by psi, the normalization. The normalization we just computed. So this will be C1 squared times H11 plus C2 squared times H22 plus 2C1 C2 H12 divided by C1 squared plus C2 squared plus 2C1 C2 times S. Now I'm going to highlight all the terms in this expression that require an integral. All these terms require integrals, and let me remind you what these terms are. So as we already defined this to be phi 1, phi 2, if I'm given the exact analytic expression for phi 1 and phi 2, then clearly this becomes integrals that are, well, let's say that are well defined, and I can use any program for three-dimensional integrals. Actually, in the end of the day, very likely these will not be three-dimensional. They will likely to be at least two-dimensional in polar angle coordinates, but in general, even if they were three-dimensional, you can use software that evaluates numerically three-dimensional integrals. Well, phi ij, we're going to be phi I h phi j, where I and j go to 1 to 2. Now, in the following, I will assume that all these integrals, these are basically 4 independent integrals because I have two independent diagonals, one independent off-diagonal term for the Hamiltonian. This one, remember, the Hamiltonian is omission, so the Hamiltonian matrix, this is just a 2-1. If the Hamiltonian elements are real, if they are complex, I should have put a complex conjugate, but in this case, I assume them to be everything to be real. And so there was going to be 3 of independent elements from here, and plus S, which is another independent number. So there are 4 3-dimensional integrals you have to compute on a computer. And I assume that, you know, your computer code has done it. Very well. Now, all I want to do is to take my expression for the expectation value of the energy, which I just derived in the previous page, a few seconds ago. And remember, this is an expression that ultimately is a function of the coefficients, C1 and C2, and take the derivative with respect to Ci and set it to 0, I equal 1 and 2. In other words, you want to look for the optimal choice of coefficients for this expectation value, or better to say, looking for a minimum. This will give rise to 2 equations, and I encourage you to do the calculation yourself. I will just state the result. The last of equation you have is C1, H11, negative E. Okay, let me write it better. So the basic point here that I want to emphasize is that by taking this will provide a system of 2 equations for 2 unknowns, C1 and C2, given a set of numbers that I've evaluated. And I can solve this equation, find C1 and C2, and get the ground state. Alternative, I can actually simply go ahead and diagonalize this matrix as we did for the double well problem, in which case I won't have a variational estimate, I will have a truncated basis approximation. So we'll, you know, we'll have less confidence on the ground state, but I will likely to have also, I will have the ground state and the first excited states. Remember the double well approximation, go back to the beginning of this lecture. And if the energy, you know, if you remember the energy after you account for mixing, one of the things that we noticed when we were solving the truncated basis expansion was the mixing was leading to a splitting of the energies. And that one of the energy was going below the estimate you get for assuming infinite barrier, that means no tunneling. Which means that the presence of tunneling of the electrons between 2 orbitals, basically the superposition of electrons or the tunneling between 2 atoms of the electron, leads to a lowering of the energy, and therefore the systems like to stay together rather than going on its own side of the story, simply because the sharing of the electron will generate a lowering of the energy. So this is a simple story of ionic covalent binding. And it's probably the simple, you see, it's a rather simple implication of toy model calculations we've done previously in this course, but with rather profound implications, because what we are talking about here is really the origin of one specific type of covalent binding. Okay, thank you for your attention, and I'll post it online.